Welcome to the deep dive. Our mission today is really to transform how you think about data modeling.
Yeah.
We're not just, throwing definitions at you. Think of this more as like an essential audio guide, almost a masterclass to help you become a certified digital architect.
Yeah.
Someone ready for, the AI-driven future.
Exactly.
Consider us your teaching assistants, maybe. We're boiling down what's essentially 44 hours of really intensive career-focused learning into this deep dive.
And this isn't just theory, right? It's meant to be a transformative journey. We're focused squarely on the tech landscape coming up, say, 2025 to 2035.
Okay.
We're skipping the history lessons, basically, and going straight for the core architectural thinking, the stuff that really underpins, everything digital transformation-wise.
Right.
We want you to internalize this so you can, instantly know the best design choice for pretty much any system you encounter.
Okay, so let's unpack that a bit, the why now factor. Because the sources we looked at, they paint a really compelling picture about future-proofing your career.
Oh, absolutely.
We're talking about mastering the very discipline that positions you as an architect in this data-driven economy. Leading tech initiatives, commanding those premium salaries, and really setting the agenda for the next, decade or two?
Yeah, easily.
It's not just a job, it seems. It's more like designing the central nervous system for the next wave of AI and computing.
And what's really fascinating, I think, is just the sheer scale of the impact. I mean, the systems you design could fundamentally change things.
Like what? Give me an example.
Okay, think about global healthcare data interoperability. Huge challenge, right?
Yeah, massive. Data's everywhere, but not connected.
Exactly. It's siloed, fragmented. A well-designed, standardized data model could potentially harmonize all that information.
So a doctor anywhere could see life-saving patient history instantly.
Potentially, yes. Imagine the impact on diagnoses. Faster, better informed decisions. It could genuinely save millions of lives.
Wow, okay. And it's not just healthcare, is it? The sources mention other areas too.
No, not at all. Think about climate change. Sustainable supply chain.
Right, tracking everything.
Everything. Every input, every route, every bit of carbon output across these incredibly complex global networks. You can't measure it, report it, or optimize it without a really robust data model underneath. It's foundational.
Okay, that makes sense.
Or financial inclusion, another big one.
How does modeling help there?
Well, many underserved populations lack access to formal banking, right? Traditional systems often can't handle maybe non-traditional transaction data or complex situations. By designing more flexible, more resilient data architectures, you can actually create new financial systems that open up economic opportunity for potentially billions of people. Good data modeling is literally the bedrock for modern social impact.
So the course structure, this is based on typically 5 major units, right? Covering everything from the basics up to data warehousing. It seems built on what the sources call a paradigm shift methodology. That sounds significant.
It is, because traditional learning often separates things out. You learn conceptual modeling first, then logical, then physical. Sequentially.
Right, step by step.
But that sequential approach, it creates this huge gap, a real disconnect between, say, the C-suite thinking conceptually about business needs.
And the developers down in the trenches thinking about SQL syntax.
Exactly. So this paradigm shift methodology says, no, you need to think multi-dimensionally, simultaneously, from day one.
Okay, hold on. Simultaneously, how does that work in practice?
It means you learn to design all 3 models almost at the same time. It forces you to constantly bridge that gap between strategy and tech.
So if I define a business rule conceptually, like customer status can only be active or inactive.
You immediately have to think, okay, logically, how does that translate? Maybe it's a status attribute with restricted values. And then physically, how is that implemented? Perhaps a check constraint on the actual database table.
Ah, I see. So you're connecting the dots constantly.
Constantly. This simultaneous thinking, that's the critical skill. It's what separates someone who just implements from someone who's, an indispensable architect.
Okay, let's stick with that architect idea. The blueprint analogy seems pretty useful here. Data modeling is like creating architectural plans for a house before you build.
It's a great analogy.
And we've got these 3 main blueprints to master: conceptual, logical, and physical models.
Right. And they're fundamentally different in their level of abstraction, But, and this is critical, they absolutely must align perfectly.
Otherwise
you build the wrong house. Simple as that.
Okay. Let's start with the conceptual model. Using our library system example from the sources, what's its main job? Who's it for?
The conceptual model is like the rough sketch, the initial high-level map. Its purpose is purely communication, mainly with business stakeholders, managers.
Yeah, okay.
It just identifies the fundamental things, the entities, the nouns of the business. So book, member, loan.
Got it.
And it shows their high-level relationships using business language, like member takes out loan.
Simple enough.
Crucially, zero technical details.
Yeah.
No columns, no keys, no data types, none of that.
Yeah.
If you show it to a business user, they should just nod and say, yep, that's how our business works.
Right. It's about getting agreement on the scope, really.
Exactly. Once you have that, then you move deeper.
To the logical model, the architectural plan. This sounds like where the real structural work begins.
It is. The logical model is, in a way, the contract. It defines the detailed structure of the data, but, and this is key, it stays technology independent.
Hey, independent.
Totally. This is where you define every single attribute, the columns, the identification strategy, your primary keys, your foreign keys, the cardinality of relationships, one-to-many, that kind of thing.
And the business rules, too.
Absolutely. All the business rules get formalized here. For our library, this is where you'd formally state, max loan period is 14 days. Or a member must have a unique ID. And the core technical goal here is normalization, structuring the data efficiently, reducing redundancy, maximizing data integrity.
So just to check I'm following, the logical model makes sure the structure is sound, the rules are clear and enforceable, but it doesn't care if it ends up running on Oracle or PostgreSQL or something else.
Precisely. It's the universal schema definition. Once that contract is solid, approved by both business strategists and technical teams, then you move to the final blueprint.
The physical model, the construction blueprint. Okay, this is where the rubber meets the road, right? Choosing materials, tools.
Correct. The physical model takes that logical structure and applies database-specific implementation details. Now, you choose your engine, MySQL, MongoDB, Snowflake, whatever it is.
And you optimize.
You optimize. You convert those abstract definitions, name, price, into specific data types with defined sizes. Varchar 50 for text, decimal 10 for money, things like that.
Right.
You also define performance boosters, like indexes on columns you query a lot. Storage specs, maybe like the InnoDB engine in MySQL for transactional integrity. And you write the actual constraints in SQL code. This blueprint is ready to execute. You can hand it off.
Okay, that flow makes sense. Conceptual, logical, physical. That's the journey. Now let's dig into the crucial grammar, the rules that hold this whole database architecture together. Keys, constraints, data types.
Yes. If the model's the blueprint, these are like the structural steel beams. They enforce those critical A to D properties, atomicity, consistency, isolation, durability, that all transactional systems rely on.
Get these wrong and disaster.
Pretty much. Your data will eventually contradict itself. It's fatal for any serious business system. So we have to start with a unique ID card for every entity. The primary key.
Right. What are the absolute non-negotiable rules for a primary key?
Okay, 3 fundamental rules must be unique. No 2 rows can ever share the same key value, ever.
Okay.
It must be not NL. Every single row has to have a key value, no exceptions.
Got it. Not null.
And ideally, it should be immutable, meaning it should never, ever change over the entire life of that record.
Immutable. Okay.
Yeah.
That's why things like names or emails are bad choices, right? They can change.
Exactly. People change names, change email addresses. That's why we almost always prefer simple system-generated integers. We call them surrogate keys, over-relying on natural keys like emails or maybe social security numbers, even though those seem intuitive.
But wait, using a surrogate key like just a number, doesn't that kind of disconnect the key from the actual business meaning? Is there a risk there?
That's an excellent point. It's definitely a design trade-off. Natural keys do have inherent business meaning, which is nice.
Yeah.
But their potential to change or maybe violate uniqueness down the line makes them really unstable foundations. Surrogate keys, on the other hand, while they might look meaningless to a business user.
Just ID 12345.
Right. But they provide incredible stability and often better performance. They're usually smaller, faster to join on. As architects, we generally prioritize that stability.
So what do you do with the natural identifiers then, like the SSN or passport number?
We still capture them, of course, but we typically define them using a unique constraint, not as the primary key itself. That way you get the best of both worlds, the stability of the surrogate PK and the business uniqueness guarantee from the natural key.
Okay, that makes sense. And sometimes one column isn't enough to uniquely identify a record, right? That's where composite keys come in.
Yes, exactly. The classic example is what's called a junction table or an intersection table, like order line item table in an e-commerce system.
Right, because one order has many products and one product can be in many orders.
Precisely. So the line item itself can't be uniquely identified by just the order ID, nor just by the product ID. You need the combination of the two.
Order ID plus product ID.
That combination forms the composite primary key. It guarantees that each specific product is listed only once within each specific order.
Okay. Moving on to foreign keys. These are the links, the reference checks between tables, preventing data orphans.
Exactly. A foreign key is the essential mechanism for enforcing what we call referential integrity. Its job is simple. Link a child table back to its parent.
So if I have an order record,
Its customer ID, foreign key, must point to an existing valid customer ID primary key in the customer table. It prevents those orphan records orders pointing to a customer who doesn't exist.
enforces the rule, no order without a valid customer.
Exactly. You can't place an order for a customer who isn't actually in your system.
Okay, this leads to a really crucial design choice when you get to the physical model. What happens if you try to delete or maybe update a parent record? The sources mention referential actions like cascade or restrict.
Yes, and this is where you often see a tension between safety and convenience. On delete, restrict is generally the safest default.
How does that work?
If a customer, the parent record, has any existing orders, the child records, the database will simply block you from deleting that customer. It says, nope, can't do that. Children exist.
So you have to delete the orders first.
You have to manually delete or reassign the orders first. It provides maximum data safety, but yeah, it requires more effort, usually from the application code that interacts with the database.
Okay, safe but more work. What about cascade? That sounds easier.
On delete cascade is definitely the convenient option, but it carries significant risk.
How so?
If you delete the customer record, the database will automatically silently delete all associated order records linked to it. No warning, no prompt.
Wow. Okay.
While this can simplify application logic, you just delete the customer and everything related disappears. One accidental deletion could instantly wipe out thousands, maybe millions of dependent records across your database.
Yeah, that sounds dangerous.
As an architect, you have to weigh that risk very, very carefully. Use it sparingly, if at all, for deletes. However, on update cascade is often much safer and frequently used, especially with surrogate keys.
Ah, okay. How's that different?
If, for some reason, a primary key value did change, which ideally it shouldn't, but sometimes systems require it, on update cascade automatically updates that value in all the child table's foreign key columns. It keeps the links consistent without manual intervention.
Got it. Let's quickly run through the other constraints you mentioned, kind of like cheat codes for data quality control.
Right. We have the simple but fundamental choice. NOL versus not NOL.
Not null means required.
Basically, yes. It signifies a field that's essential for the business process, like an order date or maybe a social security number for an employee. NOL means unknown, not applicable, or optional. Maybe a secondary phone number or a middle name.
Okay, then unique, like a primary key, but slightly different.
Yeah, it ensures no duplicates in that column, which is great for things like an email address or maybe a username. The key difference from a primary key is that most database systems allow a unique constraint column to contain one single NOL value. A PK can never have NOLs.
Ah, interesting distinction. Okay. Now, check constraints seem really powerful for custom logic.
They're fantastic, yeah. Because they let you embed custom validation rules directly into the database structure itself, rather than relying solely on your application code to enforce them.
Like what kind of rules?
Simple things like check, salary 0, or check, discount percentage between 0 and 50. Or maybe check, status inactive, pending.
But you mentioned a caution there too.
Yes, a crucial architectural note.
Yeah.
Don't go overboard with really complex check constraints. They can introduce significant processing overhead, potentially slowing down high-volume inserts or updates.
So you have to decide where the validation best lives, database or application.
Exactly. It's another trade-off. Simple, critical constraints, often good in the database. Complex, multi-field business logic, may be better handled in the application layer.
Okay, and default values, just for convenience?
Pretty much. They automatically populate a field if the application inserting the row doesn't provide a value. Ensures completeness without bothering the user. A classic example is setting order date default current timestamp. The database just fills it in automatically.
Right, makes sense. Before we leave these building blocks, you really stress the importance of choosing the right data type, especially for money.
Yes, this is absolutely critical. A rule that separates the pros from, well, everyone else.
And the rule is never use float or double add for currency or prices.
Right.
Never. Ever. Float and double data types follow a standard called IE 754. They store approximate decimal numbers using binary representations.
That sounds bad for money.
It is. Because of how computers handle those binary to decimal conversions, you will inevitably get tiny rounding errors, especially after doing calculations like adding tax or calculating interest.
And those tiny errors add up.
Over hundreds of thousands or millions of transactions, those tiny errors accumulate into potentially massive financial discrepancies. It's completely unacceptable for accounting or critical measurements.
So what's the right choice? For anything involving money, accounting, or precise measurements, you must use a decimal, PS, or numerics type. These guarantee exact precision. For example, decimal 1082 ensures 10 total digits of precision, with exactly 2 digits reserved after the decimal point for cents.
Okay, decimal for money. Got it. What about text? Why do we have char, varchar, and text? Seems like overkill for just storing words.
It all comes down to optimizing physical storage space and query performance, especially at scale. Char is fixed length.
Meaning?
If you define, say, char, and you only store the word ABC, which is 3 characters, the database still reserves the full 10 characters of storage space and padded the remaining 7 with spaces.
Seems wasteful. When would you use it?
It's fast for lookups if the data length is truly always fixed and known, like maybe a 2-letter U.S. state code, CANY. In that case, char can be slightly more efficient than varchar.
Okay, so varchar is variable length.
Exactly. Variable character. It only uses the storage space actually needed for the data, plus a tiny bit of overhead to store the length itself. Varchar 50 storing ABC uses much less space than char 50 storing ABC.
So that saves space, but you said there's a slight trade-off.
A very slight processing time trade-off because the database engine has to constantly check the length of the data. But for most text fields where length varies names, addresses, descriptions, varchar is the standard choice. It balances space and performance well.
So if the length is truly fixed, char might be better. If it varies, varchar is usually the way to go.
Precisely.
And what about text-t?
Text-t, or types like CLOB in some databases, is designed for potentially very large, unbounded blocks of text. Think of long product descriptions, user comments, articles, notes. It handles massive sizes efficiently for storage, but it's generally less efficient for searching or indexing compared to varchar, especially if you need to search within the text.
So another trade-off. An architect has to make these seemingly small decisions, but they add up at scale.
Absolutely. Optimizing these tiny details is crucial for building scalable, high-performance systems.
Okay, we've got the foundational elements down, the grammar, the materials. Now let's look at how we structure more complex systems and prepare data for analysis, maybe at a global scale. We're moving into advanced architectures, focusing on relationships and data warehousing.
Right. And modeling relationships correctly is really the heart of logical design. If you get how entities interact wrong, your system just won't capture the reality of the business.
We know the basics. 1-to-1, 1.1 is pretty rare, often for partitioning data or maybe security reasons. And one-to-many, 1M, like customer to orders, that's the bread and butter, super common.
The most common, yeah.
But let's spend a moment on normalization again, because it's so closely tied to structuring these 1MM relationships correctly. You said the goal is reducing redundancy. What does that mean in practice, especially regarding the normal forms?
Okay, normalization is essentially a set of formal rules. The normal forms, 1NF, 2NF, 3NF, etc., designed to organize the attributes within your tables in a logical, stable, and non-redundant way. At the architect level, you really need to understand the first 3.
Okay. First normal form, 1NF.
1NF is the most basic. It just requires that all the columns in your table contain atomic or indivisible values. You can't have repeating groups or store multiple values in a single cell.
So no storing multiple phone numbers in one phone number column, separated by commas.
Exactly. Each phone number would need its own row, probably in a separate phone numbers table linked back to the customer. That's 1NF. Simple but essential.
Got it. Second normal form, 2NF. This one relates to composite keys, right?
Yes. 2NF specifically applies to tables that have a composite primary key, a key made of 2 or more columns. It states that every non-key attribute in that table must depend on the entire primary key, not just part of it.
Can you give an example?
Let's go back to our order line item table with the composite key, order ED, producer DD. If you also stored the product name in that same table, the product name only really depends on the prototype part of the key, not the orderee. That's a violation of 2NF.
Ah, so the product name should be in the products table linked by productid.
Precisely. The order line item table should only contain attributes that depend on both the order and the product, like quantity or price at time of order.
Okay. And third normal form, 3NF. You said this is often the target for transactional databases.
3NF is key, yes. It builds on 2NF and adds another rule. Every non-key column must depend only on the primary key, and not on any other non-key column. It aims to eliminate what we call transitive dependency.
Transitive dependencies.
Yeah. Let's say you have a store table with store ID as the primary key, and you store the store city in that table. Fine so far. But what if you also store the store region, like West Coast, in that same store table based on the city? In that case, store region depends on store city, which in turn depends on store ID. That's a transitive dependency. Store region doesn't depend directly on the store ID primary key.
So how do you fix that for 3NF?
In 3NF, you'd pull that city to region, mapping out into its own small lookup table, maybe a cities table with city name and region. The store table would then only have the store city.
Why bother? What's the benefit?
It prevents update anomalies. If a city changes region, unlikely, but possible, you only have to update it in one place, the cities table, not potentially in hundreds of store records. It ensures data integrity and reduces redundancy. 3NF generally gives you a very stable, clean structure for transactional data.
Okay, 3NF is usually the goal for OLTP, but the biggest complexity, you mentioned, the place where people often struggle, is the many-to-many relationship.
Yes, Logically, it makes sense in the real world, like students in courses. One student takes many courses. One course has many students. But in a relational database structure, you actually can't directly implement an relationship between two tables. It's a logical impossibility for the model.
So how do you handle it?
You have to resolve it. You break it down using an intermediary table, which is usually called an intersection table, or sometimes a junction table or associative table.
Like for students and courses.
Exactly. You'd create a new table. Let's call it enrollment. This enrollment table will contain at least two foreign keys, one pointing to the student ID in the students table and one pointing to the course ID in the courses table.
Ah, so it links them indirectly.
Precisely. It breaks that one complex relationship into two simpler standard 1M relationships. You have students one-to-many enrollment records and courses one-to-many enrollment records.
And the enrollment table itself, does it have a primary key?
Often, yes. The primary key of the junction table is frequently a composite key made up of the two foreign keys, student ID plus course ID. This naturally ensures that a specific student can only be enrolled in a specific course once. You might also add other attributes to the enrollment table, like enrollment date or grade.
Got it. Resolve with a junction table. We should also quickly mention that clever but sometimes confusing self-referencing relationship.
Right, the hierarchy relationship. The classic example is an organizational chart in an employee table.
How does that work?
Well, each employee has an employee ID, which is the primary key. To show who their manager is, you add another column to the same employee table, maybe called manager ID.
Okay.
And that manager ID column is defined as a foreign key that references the employee ID column in the very same table.
Ah, so it points back to another employee record within the table.
Exactly. It's a really elegant way to model hierarchical structures like reporting lines or maybe categories and subcategories of potentially any depth without needing overly complex data structures.
Clever. Okay, let's shift gears a bit. We talked a lot about transactional systems, OLTP, but what about data analysis at scale? OLTP versus OLAP. The structural needs change quite drastically here, don't they?
Fundamentally, yes. OLTP, online transaction processing, is that normalized system we've been mostly discussing, designed for fast, day-to-day concurrent operations. Think of a cash register system needs to be quick for inserts, updates, deletes of current data.
Right. Optimized for writing and modifying.
Exactly. OLP, online analytical processing, is completely different. Think of it as the historical digital library. It's designed purely for reporting, business intelligence, analyzing historical trends. It often aggregates data from multiple different OLTP source systems.
And it's optimized for reading large amounts of data, not writing.
Precisely.
Yeah.
Queries in OLAP often scan millions or billions of rows to calculate summaries, trends, averages, so the structure needs to support that kind of reading really, really fast.
And the standard design pattern for these ORP systems is the star schema.
The star schema is absolutely the gold standard for simplicity and query speed in the OLAP world. It's very intuitive.
Describe its structure.
It's defined by a central fact table surrounded by several dimension tables. Looks like a star, hence the name.
Okay, what's in the fact table?
The fact table is at the center and contains the measures, the numbers, the quantitative data you want to analyze, things like sales amount, quantity sold, profit margin. It also contains foreign keys linking out to each of the dimension tables.
And the dimension tables are the points of the star.
Exactly. The dimension tables, the spokes, contain the descriptive attributes, the context for the facts. Dimensions like time, date, month, quarter, year, product, name, category, brand, store, location, city, region, customer demographics, segment. They describe the who, what, when, where of the facts.
Now, sometimes you hear about a snowflake schema too. How does that compare to the star schema, especially in an OLAP context? Why do we often prefer the star?
That's a classic OLA design choice. The snowflake schema is essentially a more normalized version of the star schema.
More normalized. How?
It takes the dimension tables from the star schema and normalizes them further, breaking them down into subdimensions. For example, instead of having product category and brand directly in the product dimension, a snowflake might pull category out into its own separate product category dimension table, linked back to the product dimension.
Okay, so it looks more like a 3NF structure, maybe save some storage space because you're not repeating electronics category name everywhere.
Exactly. It does save a bit of storage space due to less redundancy in the dimensions, but, and this is the crucial trade-off for OLAP, it requires more joins to answer a typical analytical query.
Because you have to join product to category, for example.
Right. To get the category name, you now need an extra join. And in OLAP, where queries scan huge amounts of fact data, minimizing the number of joins is paramount for performance. More joins generally mean slower queries.
So the star schema, even though it's a bit redundant in the dimensions,
It requires far fewer joins for most common analytical queries. You join the big fact table directly to each denormalized dimension table. This usually leads to dramatically faster query performance.
So in OLAP, we prioritize read speed over write efficiency or storage space.
Absolutely. That's the fundamental principle. We often deliberately denormalize the dimension tables in a star schema, meaning we introduce redundancy, violating strict 3NF rules specifically to improve query speed. It's a conscious design choice for analytical performance.
Okay, that makes perfect sense for analysis. Let's quickly illustrate how useful this OLAP structure is by revisiting those big 5 OLAP operations the sources mentioned, using that simple clothing store sales data cube example.
Okay, great. Imagine our data cube has dimensions for time, product, and store location.
Right. First up, drill down.
Drill down is basically zooming in,
Drill.
moving from a high-level summary down to more specific details. So if your report starts showing total sales by year, drilling down might show you sales by quarter within that year, then sales by month within the quarter.
Yeah.
You're increasing the level of detail, the granularity.
Makes sense. Going down the hierarchy, what about the opposite, roll up?
Roll up is zooming out, aggregation. You take detailed data, maybe sales of individual SKUs, specific shirt sizes and colors, and you roll them up to the product level, all shirts. Then maybe roll that up further to product category, apparel, and maybe even to total sales for the entire company. You're moving up to conceptual hierarchy, summarizing.
Okay. Drill down goes specific, roll up goes general. Now, slice and dice. They both seem like filtering.
They are, but slightly different concepts. Slice is essentially filtering the entire cube based on a single value in one dimension. For example, you could slice the cube to see only the data for Q4 2024. This effectively gives you a 2D view, like product versus store, just for that specific time period.
Okay, cutting off one dimension, what's dice then?
Dice is like slicing, but on multiple dimensions simultaneously. You're defining a smaller subcube by picking specific values across several dimensions. For example, you might dice the cube to see sales figures only for Q4 2024, and only in the California stores, and only for the shirts product category. You're cutting out a very specific chunk of the data defined by multiple criteria.
Okay. Slice is one filter, dice is multiple filters creating a smaller cube. And finally, pivot.
Pivot is about changing the orientation of the report, rotating the axis of your view. If your initial report shows, say, product category down the rows and month across the columns.
Like a standard spreadsheet view.
Right? Pivoting could swap them, so now month is listed down the rows and product category is across the columns. It doesn't change the underlying data, just how you're looking at it.
Why is that useful?
Because different perspectives often reveal different insights or trends that might be hidden in the original layout. It's essential for flexible data exploration.
Okay, theory is the foundation, definitely. But architectural skill, as you said, it's really proven when you apply it. Let's look at that practical application example. The library management system case study from the sources. It forces the learner to build all three models, right?
Yes, the library system assignment is designed specifically to mimic that real-world complexity and the need for simultaneous thinking. In the conceptual phase, the task is to identify those key business entities. The sources suggest at least 8.
Like book, member, loan.
Right. Book, member loan, author, category, maybe staff, location for branches, fines. You have to map the actual physical flow and rules of a library into abstract data objects first.
Then comes the logical phase, defining attributes, enforcing rules. This sounds trickier.
It is. This is where you define all the keys, the relationships, like book to author is MM, needs a junction table. And critically, you translate the business rules into logical constraints.
Like the borrowing limit.
Exactly. A member can borrow a maximum of 5 books at a time. That becomes a rule enforced probably through application logic, referencing counts, or maybe a complex constraint. And you have to model financial rules, like the overdue fine, 25 cents per day per book.
How do you model that logically?
Logically, you define attributes to store the due date, maybe the return date. The fine itself might be a calculated value based on those dates, or maybe you'd need a separate fines table to track specific fine transactions. The logical model has to support that calculation. And you must ensure normalization, like getting author details into an author's table, not repeating them in the books table.
Okay, and then the physical phase brings it all home. Technology choices.
Right. Now you choose your database, say, MySQL, you translate logical types, text 50 becomes varchar. Primary keys probably become int auto increment for efficiency. You define specific indexes, especially on all the foreign key columns, because joins using those keys are super common and need to be fast.
And the deliverable isn't just the code.
No, crucially, it also requires generating sample data, not just any data, but data that includes edge cases specifically designed to test your constraints.
Like what?
Like trying to check out a book when the member already has 5, inserting data for an overdue book to check the fine calculation, trying to add a book with 0 copies available, maybe even simulating a fine payment that would result in a negative balance, which your model should probably block with a key check constraint. Testing the boundaries is key.
Okay, that really demonstrates the end-to-end process. Now, to truly appreciate the kind of expertise needed out there in the industry, let's briefly touch on the complexity of some major players, mentioned Netflix, Uber. Maybe let's look at Amazon. That seems incredibly complex.
Oh, Amazon's system is an absolute masterclass in designing for flexibility and scale.
Yeah.
One of the core challenges they faced early on was building a single unified product catalog.
Why is that so hard?
Because they needed it to handle wildly different product types. Think about it. Digital music downloads, physical books, clothing with sizes and colors, electronics with technical specs, even industrial machinery. Each type has vastly different attributes.
Right. Shoe size versus processor speed, completely different things.
Exactly. The data model has to accommodate that incredible diversity, probably using sophisticated techniques like inheritance patterns, like class hierarchies and object-oriented programming, but applied to data, or maybe flexible attribute value models where attributes are stored more like metadata.
And then they went and added the third-party seller marketplace on top of that.
Which just exploded the complexity exponentially. Now, the model doesn't just track Amazon's own inventory and sales. It has to track inventory, pricing, and sales data for millions of independent vendors.
Wow.
It needs to handle financial settlements with all those vendors, manage potentially conflicting shipping options or return policies from different sellers, and somehow integrate all that diverse seller data cleanly into the central customer order processing and search systems.
While staying compliant everywhere.
While maintaining regulatory compliance across dozens, maybe hundreds of different countries and jurisdictions, it's an absolutely monumental task of data integration, normalization where needed, flexibility where required, and just sheer scale.
Okay, that definitely puts the challenge into perspective. Let's shift now to what might be the most critical topic for anyone thinking about this as a career.
Okay.
The AI revolution. The sources are clear. Data modeling is changing, like right now. Between 2025 and 2030, the architect's role is transforming.
Yeah, the immediate, most visible shift is probably automated model generation. AI systems, especially those leveraging large language models, LLMs, are moving way beyond just generating snippets of SQL code. They're starting to synthesize entire schemas.
So you're saying instead of me sitting down and drawing out an entity relationship diagram, I can just tell the AI what I need?
Increasingly, yes. You'll provide the requirements in natural language. Something like, okay, we're launching a new online grocery service. I need to track customers, their orders, the products available, inventory levels at different fulfillment centers, delivery routes, and, oh, make sure we enforce the rule that a customer can't purchase alcohol if they're under 21 in their region.
And the AI does.
The AI would then potentially generate the conceptual model outline, the detailed logical schema with tables and relationships, and even the physical schema for a chosen database. It would define the necessary primary and foreign keys, suggest optimal indexes based on expected query patterns, and maybe even generate the specific TCK constraint code to enforce that age limit rule based on customer data and location.
Wow. So it feels like the AI handles the implementation details, the how, leaving the human architect to focus much more on the strategic why.
That's exactly the shift. It's becoming augmented architecture. The human guides the strategy, defines the complex business rules and constraints, validates the AI's output, but the tedious work of generating the basic structure and code gets automated.
What else is AI changing?
Another huge area is the rise of self-optimizing databases. These aren't just static systems anymore. They use real-time monitoring and built-in machine learning to constantly analyze how they're being used.
And they adjust themselves?
Yes. Based on current query patterns, the database might automatically decide to create a new index, or maybe drop an unused one. Or it might change its data partitioning strategy on disk to better suit how data is being accessed. If it sees, for instance, that users are frequently joining the customer and order tables on, say, the sign-up date attribute, and that wasn't indexed,
The AI just creates the index.
the AI can automatically create the optimal index for that join without any human DBA needing to intervene. It ensures performance stays high even as business needs and query patterns evolve dynamically over time.
That's incredible. Now, there was one piece we didn't talk much about earlier, but the sources highlighted as critical for the future architect: privacy by design.
Absolutely essential. In today's world, with GDPR, CCPA, and countless other regulations, privacy can't be bolted on afterwards. It has to be fundamentally engineered into the data model right from the very beginning.
How do you model for privacy?
It means architects need to understand and integrate more sophisticated techniques directly into the design. For example, think about zero-knowledge proofs or similar cryptographic techniques. These allow an organization to verify something about data, like, is this user over 18, without ever actually needing to see or store the sensitive raw data itself, like the user's exact birth date. The model needs to support storing proofs or results, not necessarily the raw data.
Okay. And you also mentioned federated learning. How does that fit in the modeling context?
Federated learning is crucial, especially for global companies dealing with sensitive distributed data, like in healthcare or maybe personalization on mobile devices.
Right.
Instead of pulling all the raw, sensitive patient data from thousands of hospitals into one giant, high-risk central data lake for analysis.
Which sounds terrifying from a privacy perspective.
Exactly.
Yeah.
With federated learning, the machine learning model itself is distributed out to the local data sources, the hospital's, the user's phone. The model trains locally on that sensitive data and then only sends back aggregated, anonymized insights or model updates to the central server.
So the raw data never leaves its protected local environment.
Correct. The architect's job then is to design the data schemas and the system infrastructure to actually support this decentralized training and aggregation process, ensuring privacy is preserved structurally.
Okay. One last major trend: the democratization of this field. Visual and no-code modeling tools. The citizen data modeler.
Yeah, this is huge. Tools like Airtable, Notion, maybe the Microsoft Power Platform, they're empowering people who aren't traditional developers or DBAs.
Yeah.
The business users, the subject matter experts who actually understand the data requirements best to build surprisingly sophisticated relational data models themselves.
Using drag and drop.
Mostly, yes. Drag and drop interfaces, visual relationship builders. They can create tables, define columns and data types, establish links between tables, even set up basic constraints, often without writing a single line of SQL code.
What's the business impact of this? Is it just making things easier, or is there more to it?
The impact is potentially enormous. The sources suggest dramatic increases in development speed, maybe 85–90% faster in some cases, and significant cost reductions, like 60–80%, compared to traditional workflows where requirements go back and forth between business and IT.
Because you cut out the middleman, essentially.
You cut out that slow, often error-prone translation process. When the business user can directly model their own reality, you get faster deployment, iterate more quickly, and often achieve much higher initial data quality because the person building the model deeply understands the domain.
Wow. Okay, this has been an incredibly detailed journey. We've gone from the absolute fundamentals, the blueprints,
Conceptual, logical, physical.
right up to the crazy complexity of global companies like Amazon, and now looking at how AI is reshaping everything.
Yeah, we covered those three essential blueprints. Conceptual is the business map. Logical is that technology-independent contract, really emphasizing getting to 3 and F for transactional systems. And physical, the specific database code, where you optimize types like using decimal for money and make those crucial choices like cascade versus restrict.
And we stress the non-negotiables for primary keys: unique, not null, immutable ideally, and the power of constraints.
Definitely. Then we zoomed out to systems at scale, mastering that junction table to resolve many-to-many relationships, and understanding how OLAP systems use the denormalized star schema and those big 5 operations: drill down, roll up, slice, dice, pivot to turn mountains of historical data into actual business intelligence.
And the timing seems absolutely critical here. You said data modeling is at a real inflection point.
It really is. The sources strongly suggest that organizations and individuals who strategically embrace this AI-augmented approach to data architecture, who integrate privacy by design from the start, who master these concepts in the next, say, 5 years, they're likely to be the ones dominating their industries for the next 20.
Which brings us perfectly to our final provocative thought, something for you, the listener, the aspiring architect, to really chew on. The sources make it incredibly clear. The most valuable professionals in the coming decade won't necessarily be the ones who can write the most complex SQL by hand. It'll be those who can bridge human insight, understanding the strategic why, the business needs, the ethical considerations, what with AI's rapidly growing ability to handle the technical how, the implementation details.
Right. The machines are getting really good at the mechanics, optimizing indexes, generating basic schemas.
So the question for you is, are you ready to embrace that evolving role of the AI data architect? Are you ready to shift your focus towards complex business strategy, towards integrating disparate systems, towards ethical design and governance, while leveraging AI to handle more of the underlying implementation?
Because that shift in focus from pure technical implementation towards strategic, ethical, and integration-focused design, that really is the definition of the future-proof career we've been mapping out today.
An essential skill for the future. Thank you so much for walking us through all of that.
My pleasure. It's a fascinating time to be in this field.
And thank you for joining us on the deep dive. We hope this guide helps prepare you for the revolution that's already underway.